Okay, so question number 3 is asking, check whether the relation R. You want to question exercise number 3. Exercise number 3 is check whether the relation R defined in the set, the relation R defined in the set, 1, 2, 3, 4, 5, 6 as R is equal to all the order pairs A comma B such that B is equal to A plus 1 is reflexive, symmetric, or transitive. If it is reflexive, symmetric, or transitive. Okay, so if you want to basically write the relation R basically if you want to write the relation R in this set, let's call the set A, and basically B has to be A plus 1. B has to be A plus 1. Okay, so now in order to decide whether R is reflexive, what you can do is that basically the rule that we are using in basically if A comma B belongs to R, if A comma B belongs to R, then B is equal to A plus 1, which means that B is not equal to A, of course, which means that B is not equal to A, right? B is not equal to A, and which means that basically A comma A does not belong to R, right? And which means that basically R is not reflexive. R is not reflexive. Another way of saying the same thing is that basically if you take this set over here and basically take all of the elements of A as ordered pairs, meaning that normally what you would do is that you would write A as basically, for example, 1, 2, you know that 1, 2, 3, 4, 5, and 6, right? And so these are all the members of A. That means that R is basically the collection of all of these ordered pairs, where A, of course, belongs to A, meaning that A can be basically 1, and if A is equal to 1, then basically B is equal to A plus 1, which is 1 comma 2. And if A is equal to 2, then B becomes 3. If A is equal to 3, then then B becomes 4. If A is equal to 4, then B becomes 5. If A is equal to 5, then B becomes 6. And there you have to stop because I cannot write, for example, 6 comma 7. 7 does not belong to A, right? So what that means is that 5 comma 6, basically these are all of the members of R. And you can see that there is no member in R such that the first component is equal to the second component of the ordered pair, such that the first component is equal to the second component in the ordered pair. Therefore, A comma A does not belong to R. And therefore R is not reflexive, right? R is not reflexive. Now, in order to show that R is symmetric, R is not symmetric, it's easy to show that, for example, 1 comma 2 belongs to R, but 2 comma 1 does not belong to R. Basically, you can say that 1 comma 2 does belong to R, but 2 comma 1 does not belong to R, based on what we have seen, what we have written over here. And therefore R is not symmetric. So that is that. Now over here you can see that, for example, in R, if you want to show whether R is transitive or not, you can see that basically 1 comma 2 belongs to R and 2 comma 3 belongs to R. And 2 comma 3 does belong to R. But 1 comma 3 does not belong to R. Therefore R is not transitive. So that was question number 3. Question number 4 is basically you want to show that the relation R in R, defined as question exercise number 4, you want to show that the relation R in R, which is basically real numbers, in R defined as R is equal to, and of course you see that this is basically, this is R, defined as R is equal to all the ordered pairs x comma y such that A is less than or equal to B, is reflexive and transitive, but not symmetric. Right? So in order to show that, you want to show that basically R is reflexive. So in order to show that R is reflexive, basically we are working with the set of real numbers, and the relation is all the ordered pairs x comma y such that A is less than or equal to B, right? So A is less than or equal to B means that basically A can be less than B, which means that it cannot be reflexive. Well, of course, yeah, okay. Well, by this definition here, you can argue that R is equal to basically all the ordered pairs A comma B, or such that A is less than or equal to B, and so in this case, clearly A comma A belongs to R because A is less than or equal to A. As A is less than or equal to A. Therefore R is reflexive. Therefore R is reflexive. Now, in order to show that basically is symmetric and transitive but not is reflexive and transitive, okay, so basically we have established that basically R is reflexive. Now to show that R is not symmetric, is not symmetric, what you can say is that, of course, here basically R is equal to all the ordered pairs x comma b, x comma y, such that, for example, x is less than or equal to y. So for example, you can argue that 2 comma 4 belongs to R as 2 is less than or equal to 4, right? But 4 comma 2 does not belong to R as basically 4 is not less than or equal to 2. is not less than or equal to 2. Equal to 2. And so basically you can say that R is not symmetric. And to show that R is transitive, to show that R is there was one number 4 actually. To show that R is transitive, so what you can say is that, of course, let some x comma y belong to R, and let some x comma y comma z belong to R. Now this implies that x is less than or equal to y, and y is less than or equal to z, right? So if x is less than or equal to y and y is less than or equal to z, that implies that x is less than or equal to z, which means that basically x comma z does belong to R, which means that basically R is transitive. R is transitive. And when you when your argument is of this form, this is a proof and nothing, and basically no counter example can be produced against your argument, because well, your argument is done using algebra. So there is really no way to go against this argument. So that was question number 4. Now question number 5. Question number 5 is let's do some new layer here. 24. Okay, so question number 5 is you want to check whether the relation R in R defined by R is equal to A is less than or equal to B cubed is reflexive, symmetric, or transitive. Okay, so you want to check whether exercise number 5, you want to check whether the relation R, in R, basically R in the set of natural numbers defined by R is equal to, or the order pairs A comma B, such that A is less than or equal to B cubed, is reflexive, symmetric, or transitive. Is reflexive, symmetric, or transitive. So in order to check that, so first of all you want to know whether R is reflexive. So based on the set R, we say that basically R is all the order pairs A comma B such that A is less than or equal to B cubed. That means that A comma A cannot belong to R, well, simply because A is less than or equal to B cubed. When A is less than or equal to B cubed, what that means is that A cannot be equal to B, right? If A cannot be equal to B, then A comma A cannot belong to R, which means that R is not reflexive. R is not reflexive. Now, okay, so, and you can basically, my argument was using logic, only logic. You can also say that, for example, it is observed that basically, for example, or you can say that it can be observed that 1/2, 1/2 does not belong to R, since basically 1/2 is greater than 1/2 cubed, right? 1/2 is greater than 1/2 cubed, and so R is not reflexive. Sometimes it's not easy to find this. This you would call a counterexample. And sometimes, well, it's easy to find a counterexample, and if you find one counterexample, that means that basically you have proof that whatever the case was is whatever you want to show or not show is just simply not true, because it's not true in at least one case, right? Sometimes it's not easy to get the counterexample. Sometimes the situation is a little bit tricky, and in those cases, in some of those cases, it's easier to use logic. If you can use logic, of course, you will always use logic. Otherwise, if you can use a counterexample, then you will use a counterexample. Sometimes none of those options is really easy. Then you will have to find somebody, to basically to show that, to prove what it is that you want to prove, right? So that means that R is not reflexive. Now, to show that R is not, to show that basically for the case that R is whether or not symmetric, now this is a little bit tricky using logic, because the condition is actually a little bit tricky. Meaning that if I, for example, argue that, for example, let x comma y, some x comma y belong to R, and actually not. Okay, so let's see. So let's say that some x comma y belongs to R. That implies that x is less than or equal to y cubed, right? That means that x is less than or equal to y cubed, right? And in order to show that basically R is symmetric, we need to show that y comma x also belongs to R, meaning that y is also less than or equal to x cubed. Which is not possible, because when x is less than or equal to y cubed, when x is less than or equal to y cubed, then, but of course you need to be not so quick about deciding those such things. Let me see. Okay, so as you can see here, basically if I assume that, for example, x comma y belongs to R, that implies that x is less than or equal to y cubed. Now, based on this, you need to be able to show whether now, based on this assumption, you need to show whether y is less than or equal to x cubed as well. Now, I'm not really very basically, when it comes to inequalities, you can use number lines and decide everything very clearly. You have no problem there. But then when it comes to number lines and the square of some numbers and cube of some numbers, then things get a little bit complicated and you can make mistakes, right? So it's not easy to decide if x is less than or equal to y cubed, or at least I cannot do it right now, really. What I mean to say is that I cannot really, I'm not really able to decide whether x is less than or equal to y cubed. If that's my assumption, if that implies that y is less than or equal to x cubed, right? So, in order to solve the problem for now, what you can do, you can just simply create a counter example. Which would be basically as valid as basically using logic and algebra in order to prove whether basically something is the case or not. So over here we are saying that x is less than or equal to y cubed. That means that if basically 1 comma 2 belongs to R, or there is actually no if, that is actually a valid statement. 1 comma 2 does belong to R because basically 1 cube is less than, or I'm sorry, because basically 1 is less than 2 cube. Because actually 1 is less than 2 cube, which is equal to 8. So that means that 1 comma 2 does belong to R. But then you can argue that but 2 comma 1 does not belong to R, since 2 is basically 2 is greater than 1 cube. 2 is actually greater than 1 cube, which is equal to 1. 2 is greater than 1, and it's supposed to be less than or equal to basically whatever you have over here. Which means that using just one simple counter example, we have proved that basically R is not symmetric. Now, in order to show whether R is transitive or not, since I'm dealing with basically an inequality and the third power of some variable, I'm going to use a counter example. So for example, you know that for example 1 comma 2, we argued before that it belongs to R. And also 2 comma, for example, 3, does belong to R, because 1 is less than or equal to 2 cubed. 2 cubed is equal to 8, so 1 is less than 8. And 2 is less than or equal to 3 cubed, which is equal to 9. I'm sorry, 27, right? So this is actually the case. Now, 1, 3 does actually belong to R. Does actually belong to R because 1 is less than or equal to 27, right? So normally, so basically this shows that, so this is supposed to show that basically R is transitive, but that's not the case. You need to be careful there. When you're creating a counterexample, or any sort of example for that matter. When you're creating some example in terms of numbers in order to show anything, that example has to be is supposed to be devised in such a way that it possibly negates that statement, right? Otherwise, for example, you can see over here that, for example, 1, 2 does belong to R, 2, 3 does belong to R, and 1, 3 does belong to R. So then logically I would be able to say that R basically is transitive. R is transitive, right? But that is actually not the case. R is actually not transitive, because there is at least one counterexample that you can find that shows that R is not transitive. And what is that counterexample? And as I argued before, it's not always easy to find that counterexample. So in such cases, you need to somehow use logic in order to decide whether basically something is the case or not. And then if your logical argument is very complicated, then using that argument, you can just simply create one case of a counterexample and then use it as your argument, and then everything is proved, right? Now, in this particular case, using a logical argument is not easy, because you are dealing with an inequality and a third power on a variable. So it's not something that at least I can do right now. So what I'm going to do is I'm just simply going to give you the counterexample, which I have read off of the solution, right? And hopefully sometime in the future we will learn more about these inequalities and how to deal with them more effectively. So basically 3, 3 halves and 3 halves, 6/5. So you can see that these are not the kinds of things that you can just normally get to. It does need a lot of contemplation and a lot of considering all different cases, right? So these belong to R, because you can say that basically 3 is less than 3 halves whole cube. So 3 halves whole cube is the same thing as, so 3 is less than 27 fourths, and 27 fourths is something like, for example, 4 times 5 is equal to 20, 4 times 6 is equal to 24, 4 times 5 is equal to 20, 4 times 7 is equal to 28. 4 times 7 is equal to 28, and 4 times 6 is equal to 24, right? So that means that 27 fourths is some number between some number between 6 and 7. So 27/4 is some number. This is some number between 6 and 7. So this is some number between 6 and 7, which means that basically 3 is less than that number, whatever that number might be, right? And to basically to check this part, you can say that basically 3/2 is less than 6/5 whole cube, which basically you can say that 3/2 is less than 6 cube is equal to 36. 36 times 6 is equal to 36, and 216 and 5 cube is equal to, I suppose, 125. So 216, 125, that's some number like, for example, 1 point something. There's something actually wrong here, either with my calculation or, so let me see, 6/5 whole cube. 6/5 whole cube is equal to 1.7. Well, okay, 1.7, that's 216 by 125 is 1.7. And 3/2 is the same thing as 1.5, so 1.5 is less than or equal to 1.7, right? So that is 216 by 125, which is approximately 1.7. So that is also true, right? So that is also true, which means that these two numbers do belong to R, because in each of these cases x is less than or equal to y cube, right? In each case x is less than or equal to y cube, and that is the reason why that is the case, right? Now what you basically if R is transitive, then let's see if 3/2 and 6/5 also belongs to R. So 3/2 and 6/5, 3/2 comma 6/5. So you have 3/2 and basically you have 6/5 over here. You have 6/5 over here, whole, and raise it to the third power, you'll get 216 by 125, right? Which is approximately 1.7. Now no, I'm sorry, I'm supposed to take this number actually. So 3 and 6/5, right? So 3 and 6/5. So we argued that 6/5 is approximately 1.7. But as you can see, basically 3 is greater than, so 3 comma 6/5 does not belong to R, because 3 is actually greater than 6/5 whole cube, right? Which means that basically, R is not transitive. Now, as I mentioned before, it's not really easy always to get to these counter examples. And since we do not, or at least I do not have the tool the logical tool to use algebra in order to decide I mean, I do not have the algebraic tools in order to use basically some third power of some variable and basically inequalities. For now, all that we can do is that we can use the counter example that we found in the solution, but then the only way that remains in order to solve such problems is to actually be able to use algebra in order to decide what is the case in such cases. And so we will make sure that we will use the concept of inequality at least all the way up to the end of the whole roadmap, right? So that is basically that. So that was question number 5. Now there is question number 6 as well, or exercise 6, which is show that the relation R in set 1, 2, 3. Show that the relation R in the set 1, 2, and 3 given by 1, 2. So this is your R basically, 1, 2 and 2, 1 is symmetric but neither reflexive nor transitive. Is symmetric but neither reflexive nor transitive. Okay, so about this question, we have show that the relation R in the set 1, 2, 3 given by this relation is symmetric but neither reflexive nor transitive. So to show that it is symmetric, of course you can see that basically 1, 2 belongs to R, and also 2, 1 belongs to R. And so therefore you can say that R is basically symmetric. R is basically symmetric. Now, in order to show that it's not reflexive, basically you can argue that, for example, 1 belongs to A. Let's call this, for example, the set A. So you can argue that 1 belongs to A. That 1 belongs to A, but 1, 1 does not belong to R. Therefore, basically R is not reflexive. Therefore, R is not reflexive. Right, so that is basically that. And also you can show that it's not basically transitive. Show that it's not transitive. You can argue that, for example, 1, 2 1, 2 belongs to R. 1, 2 does belong to R, and 2 comma 1, and 2 comma 1 does belong to R, but basically 1 comma 1, but 1 comma 1 does not belong to R, which means that R is not transitive. R is not transitive. So that's question number 6, for example. Now question number 7 is show that the relation R in the set A of all the books in a library of a college given by so you want to show that this is number 7. Show that the relation R, in the set A, of all books in a library of a college, given by R is equal to basically all the order pairs x comma y, such that x and y have the same number of pages. X and y have the same number of pages. So this is your set R, is an equivalence relation. So to show that a relation is an equivalence relation, you have to show that it's reflexive, symmetric, and transitive, and that means that it's an equivalence relation. So reflexive basically well, you can argue that x comma x belongs to R, I don't really know how I can make that assumption that two books having the exact same number of pages do exist. Let me see. Well, basically the way that I was thinking about this was actually not right. So the way that you can think about this, basically the condition for reflexive is that x comma x has to belong to R for all x belonging to the set A, right? That is the condition, and this condition will be fulfilled for each and every book in the library, because every book in the library has the exact same number of pages as itself, right? Therefore, you can say that x comma x belongs to R as x and x has the same number of pages, because x and x has or have the same number of pages. So since x comma x does belong to R, that means that basically R is reflexive. Now about R being symmetric, you can argue that suppose that there is some let basically some x comma y belong to R. So that basically implies that x has the same number of pages as y, right? So x has the same number of pages as y, which means that y has the same number of pages as x, which implies that y comma x does belong to R. Now x comma y belongs to R, y comma x belongs to R, and therefore R is symmetric. That is basically for R being symmetric. About R being transitive, you can argue that let some x comma y and y comma z belong to R. That implies that basically x has the same number of pages as y and y has the same number of pages as z, which means that x has the same number of pages as z. Which means that x has the same number of pages as z. Which means that x comma z does belong to R. And since x comma y, y comma z belongs to R, and x comma z also belongs to R, you can say that x is transitive. Now, we argued that, R is transitive. So now R is reflexive. R is reflexive, symmetric and transitive. And therefore R is an equivalence relation, right? So that was question number 7. Now question number 8 is basically show that the relation R in the set A, that the relation R in the set A, which is equal to 1, 2, 3, 4, 5, and that's it, given by all the ordered sets, given by R is equal to all the ordered pairs A comma B, such that the absolute value of A minus B is even, is an equivalence relation. Show that all the elements of 1, 2, 3 are related to each other. Show that all the elements of the set 1, 3, and 5 are related to each other. And all the elements of 2, 4 are related to each other. Right? But no elements of 1, 3, and 5. But no elements of 1, 3, and 5 is related to any of it. Is related to any of the elements of 2, 4. Right? So that is the question here. So since this is going to take some time to basically to solve, we will solve this question in the next video. I'll see you in the next video.